the largest slide deck of the conference at 1 GB, so I hope you enjoy that.
You need to freestyle it.
Okay. Oh yeah, we're just setting up a little bit. Okay, we're ready to start.
Är det laserpekare också? Hello. Thank you. So welcome to our talk about ray tracing voxels. And before we start, can we get an image on the screen in the front here, if possible? I'll just start anyway, and let's hope it resolves. Thank you. Actually, could we get the one with the notes on? Yeah. Anyway, so welcome to the talk. My name is Gustafsson. I'm the founder and CTO of Tuxedolabs, and by my side here, Gabe Rundlett, our very talented graphics programmer. And we're going to talk about two things. It's going to be a talk that is split up in two parts. First, I'm going to talk about the techniques I used for implementing the rendering of voxels in Teardown. And the other half of the talk, Gabe is going to talk about a new engine that we've been working on for some time. And let's see. Which one do you prefer? So let's see if we have a movie coming up here. Presentation is on a Mac. Next year we're going to do Windows. All right. So here's a little movie clip from Teardown for those who don't know. It's a sandbox heist game in a very dynamic voxel world where everything is destructible, and it uses ray tracing for all the lighting, despite being a relatively old game. It came out in 2020, so ray tracing hardware hadn't really taken off at that time. And it uses a custom physics engine and a custom graphics engine. Everything is just specially written for this game, it also has a pretty big modding community, so you can build custom content with it. So we have to support a lot of arbitrary cases. It's written in OpenGL, or was at least, mostly because I didn't know better when I started. And I'm also not really much of a graphics programmer. I'm more of a generalist or a physics programmer. This is what I had at hand. I was also implementing this on a Mac, so everything had to be OpenGL 3.3. So I didn't really have compute shaders. So everything you see or saw there was implemented in using the normal rasterization pipeline with vertex shaders, fragment shaders, and textures. So how did I do that? And let's start with just a single voxel object. And the voxels here are represented as a 3D texture on the GPU. It conforms to a box like this. And to put it on the screen, we rasterize the bounding box. So there are 12 triangles. They're drawn with front-face coloring, so we draw actually the backside of the box. And if we imagine a camera being behind the boat, seeing the backside of the boat here, in the fragment shader, you would compute just the ray going out through that fragment to see, and then use an analytical function to see where it hits the bounding box on the backside. We also know where it hits the other side of the box, because that's the rasterized point. Once we have those two, we can just step through the voxel data, or the texels, the 3D texels in this case, until we hit something. And the way the data is stored in Teardown is that we use 1 byte per voxel to save memory, and then that is looked up in a palette on the side. So we get all the surface properties like RGB color, roughness, metallicity, and things like that we get from the palette. And the algorithm is called fast voxel traversal by Manatized and Wu from 1987. It's very similar to a line drawing DDA algorithm, but it makes sure to visit all the cells that the ray passes through. So you start at the cell where the ray enters the box, and then you just look on which side or which face it exits through, and you take a step in that direction, and you just continue that until you hit something. So in this case, we would walk right, and then it passes through the downwards phase. You take a step down, and then right again. And if we take a step right now, we would hit something, so we know that's where the ray can be terminated, and we get the depth from the geometry. By traversing it this way, we can also record what was the last direction we took before hitting something, and in this case, we were walking right. That means the normal has to be facing the other direction. So we get both the distance, the normal, or distance is depth in this case, depth, normal, we get the properties from the palette, and then we basically have everything we need to fill in the G-buffer. As you can imagine, if you have a very sparse shape, like the top of this pine tree, you would have to step through a lot of empty space just to find out you didn't hit anything, and that's rather expensive. So in order to accelerate that, what I do in Teardown is to compute a number of MIP maps and use them basically as an octree acceleration structure. So we step in the lower MIPs first, and then if we hit something, we switch to a more fine-grained level of detail for that object, and then if we still hit something, switch to the actual data. Or we can also go back to the one before and kind of work our way up and down the MIP chain as we traverse the voxel object to finally get an actual hit. And that's the way we accelerate the search. Oh, this was a dark image. So now that is how you do, or how we rasterize voxel objects in a relatively fast way using these MIP maps to accelerate skipping over empty space. And then we also need, of course, if we want to draw the whole world with this, we need to have a way to make this efficient for multiple objects. And overdraw is pretty expensive here because we cannot really use a lot of features of the rasterization pipeline, like early C-calling, because finding the depth of the fragment we're shading is part of the slow path, so to speak. We have to step through all that voxel data before we get the depth. We can't really do a depth pre-pass like you would in these scenarios where overdraw is expensive. And if we look at the bounding boxes here, we can see that there is a fair amount of overlap here. This is just the bounding boxes for the ones closest to the camera. It's actually way more behind the buildings, so it's usually around 1,000 or a few thousand shapes on the screen that you see. at any one time. And the way you can solve that in a number of different ways, and the one I picked for Teardown was to use binning. So I divide the objects up into, categorize them based on their distance from the camera or their depth, and draw the first bin in one pass. I make a copy of the depth buffer, and then when drawing the next bin, I can kind of compare the distance. If there's nothing in the depth buffer, I have to traverse the object. If there is something in the depth buffer already, I compare that depth to the point where the ray intersects the front face of the bounding box. And if that is further away, there's no way this is going to be visible on the screen, and we can just terminate the ray early at that point. And then you can repeat that for every bin. And here's a little visualization of that. This is the first bin. And then if we draw the next bin, we can kind of see behind the building on the left there, you can see a little house sticking up. Only the roof part of that was actually, we needed to traverse through the voxel data, and all the rest we could just early out. So that's a really good optimization. And we just work our way through the bins until the whole image is fully drawn. And that's pretty much it for putting for filling in the G buffer. So we have a fast way of rasterizing an object using MIP maps as an acceleration. Then we use the binning to accelerate the drawing of many objects, and we have the G buffer. And we haven't really talked about lighting. This talk is not really about lighting, so I'm not going to say that much about it. But now that we have a way to rasterize voxel objects, we could theoretically use any method of any traditional way of doing lighting. We could use cascaded shadow maps. We could use screen space reflections by traversing the depth buffer and all those tricks. But we can't really do any pre-computed lighting, so we wouldn't really have these nice soft lighting that we were after, that you can see on the right side. And I also kind of enjoy trying to do things a little bit differently. So I really wanted to try and do ray tracing, even though it's in OpenGL. And the method I came up with, I call the shadow volume. It's probably been done before, but it's the way it's very suitable for voxels. So what I do is I have kind of a dual representation. So apart from these objects that are oriented, I also have a separate representation on the GPU, which is a giant 3D texture covering the entire level, one texture, where an entry in that volume basically represents whether light can pass through or not, whether it blocks light. So it doesn't contain any color information or anything. It's just like, does this point in space block light or not? So here it would, and here it wouldn't. And of course, this has to be then resampled in some way from all these individual objects with rotation into something that is axis aligned in a single texture. And that also needs to be updated, as you can imagine, when things move around and get added and deleted and destroyed and whatnot. It also consumes a lot of memory because it needs to cover the entire level, and it's not compressed, almost. So in this case, this is an actual Teardown level. It's 400 meters across, 3,400 on the other side, and 290. Well, there are 10 voxels per meter, so 400 meters is 4,000 voxels. If you sum this up, it's going to be around 4 billion voxels in this scene. And if we were to store them the same way we stored voxels in the objects, that would be 4 gigabytes, which is a bit much, especially at the time. But then we can use the fact that it's just representing whether it blocks light or not, which is just a binary value. So you can pack 8 voxels into a single byte. And by doing that, we can cut the memory requirements from 4 gigabytes down to 500 megabytes, which is a more reasonable size to put in the VRAM. And then, as I said, this needs to be dynamically updated, and because the GPU here doesn't really have that much information about the scene, it just gets draw calls from the CPU and does what the CPU says it should do. We can't really do this on the GPU. It has to be done on the CPU because that's where we have the acceleration structures and all the information needed to generate this. That also means we're going to have a lot of complex code for doing this continuously, and not too much and not too little. So we have to track all the changes in the world. We have to distribute that over multiple frames and all that, and make sure we don't miss anything, so things get out of sync. And this is a little video demonstration of how it works and what it looks like. So when something rotates, you're going to get these quantized voxels. The voxel size is the same as the ones in the object, but of course they're not rotated, so it's going to be a lot of quantization artifacts, as you can see. But you don't really see that much of this in the shadow if you just use soft shadows for everything, which we do. And this also, of course, associated with a performance cost, especially if we have a lot of dynamic objects, or if there is a lot of things going on in the scene. This can have a considerable performance impact on the CPU. And by using this shadow volume, if we have a point in space, say we want to shade a point here, we would just translate that to where is this in the shadow volume, and then we can just step through the voxels and see if we want to trace to that light. If we can trace that distance without hitting anything, we know that that point would be lit, and that's essentially what we do. And we can use just normal or regular standard methods for doing ray traced lighting, and we use a lot of stochastic variants. We use blue noise a whole lot for this. And I'm not going to talk about the specifics. It's not very unique to Teardown. It's using a lot of standard methods. This one shows the direct lighting and ambient occlusion. And we also do use this shadow map for computing reflections. Worth noting here is that since it's a bitmap, it's essentially a huge 3D bitmap. We don't have any contact information. When we hit something, we don't have a hit information. We don't know the color, we don't know the normal, we don't know anything. So we can't really do a secondary bounce with this. We cannot do path tracing. That also means we don't really know the color of what's in the reflection, but we do use some screen space information where it is available. And where it's not available, we still get really good specular occlusion. For when you're outdoors, you can really, that is the most important part of the reflection, I would say. And then we have the volumetric light. We also use the shadow volume for that. It's a pretty expensive pass that we do per light source and then accumulate them. We do this in half res, actually, in Teardown. Oh, that's also a very dark image. And then we denoise these channels with separate denoisers for all the channels. Pretty standard spatiotemporal denoisers. They sample in a spiral pattern and accumulate. And then we apply some TAA in the end, and we get something like this. This way of traversing the shadow map, it comes with a lot of problems that we're going to talk about in a minute. But one thing that's actually really good about it, or two things. One thing is that for short rays, if we're just gonna shade a position in space here and see if it hits by that light, if the ray is short, we're just going to take a few steps in this 3D texture and see that we hit something, and we can terminate early, and it's going to be super fast. The problem is, of course, if we have really long rays, we're going to have to step through the exact same problem as before. So we actually apply the same optimization with building MIP maps and use them as an octree to accelerate the search. But one really cool thing, the other really cool thing about this way of doing ray tracing is that we can traverse that shadow map in several different ways depending on how good of a quality we want for that particular ray. And we can select this per ray, but we can also select it per, we can switch it while tracing the ray, which we'll see in a minute here. So if we want to do a high quality trace, say we do a sun, a ray towards the sun, for instance, we want really as sharp shadows as we can, and we don't really want to miss features when we trace. So we can just use that same fast voxel traversal algorithm as we talked about before, and it's going to be very exact. But in Teardown, for some effects, we do a much simpler traversal where we just take a fixed step along the ray and check whatever is in that voxel, or in that cell. That means we can sometimes miss information, like in this marked with a question mark here. The ray skips over the corner, it kind of cuts the corner through, but we don't never look in if there is anything in that cell. And that, of course, is gonna give some artifacts. And we can see that it's used for reflections, at least on some quality settings in Teardown. And you can, if you look closely in sharp reflection, you can kind of see these jagged edges here. That is a direct artifact from traversing it this way. We also have a even lower quality trace, which starts out in the beginning of the ray. For some effects, we use this for ambient occlusion, for instance. In the beginning of the ray, it's important that you get a very exact geometry information because you want nice, crisp contact shadows. But the further out you go, the less important it is that a hit is exact. So we can start in the highest quality trace mode, and if we don't hit anything, we can just switch over to a lower quality one, step a little further. If it still doesn't hit anything, we can double the step size and walk down the MIP chain to level 1 or level 2, and get a much, kind of a dynamic level of detail depending on how far away the thing we hit would be. And this is something that's pretty hard to do with modern hardware ray tracing, which I think is a slight advantage with this method. But it's we should also talk about the downsides because there are quite a few. I'm not going to talk that much more about how a frame is built in Teardown, but there are 2 excellent blogs that do this in detail that I've listed here. If you either take a photo or if you just Google Teardown frame breakdown, you're going to find both of them at the very top. And the top one here is written by Stephen, who I've never met, but I know is in the audience today. So thank you for that, Stephen, wherever you are. It's been helping a lot. Yeah, thank you for not so I didn't have to do that myself. Let's talk about the limitations of this method. And we already touched upon a few of them, one of them being the sparse shapes. They're very inefficient to render because you have to step through this empty space. So we want to optimize the shapes so that they contain as little air as possible. In a worst case scenario like this, you can't really split it up. It's always going to be air, otherwise you're going to end up with very many shapes. This splitting up, if we split it up too much, we're going to get way more shapes, and that's going to push more draw calls. So it's also bad to have too many shapes. And this way of juggling the sparsity versus the number of shapes is something that the artists and level designers do manually today, which is a really complicated task because they don't really know what to optimize for because it's 2 different things to optimize for. So getting rid of that would be really nice. This thing stopped working. Can we get the next slide? Oh, thank you. Another limitation is the palette that we talked about. We only have 255 possible colors for a voxel, and that is per shape. We're not using a global palette for all the shapes, but per shape we have 255 colors. That in itself is usually more than enough for an artist to express what they want to do for an object. But a cool thing with voxels is that you can, once we have that, we would want to use that for procedurally changing that during gameplay. And we do that just a couple of times. One of them is the skid marks. You can see here. We can turn a voxel and we can make it more black. It's also used for fire and explosions. And we also actually have a little spray can that you can paint things yellow, but it's only one color. And there's a reason for that, and that is because we statically, at load time, we pre-compute for every color in every shape, we pre-compute fixed gradients from that color to yellow, and from that color to black, and then from yellow to black. And that has to be done for every material. So we can't really use all 255 colors in the actual object, because then there wouldn't be anything left for the gradients. So we only use like 20, 25, 30 colors for the actual object. So this is quite a limitation. If we just had the ability to procedurally set any color we want for any voxel, that would open up so many possibilities. We also have the level size limitation that we talked about already. It hasn't been that much of a problem in Teardown, but depending on the game or mod, that is a big limitation. And it would just take a lot of memory for large levels. Global illumination, as we also talked about, since it's a bitmap, we can't store any information, we can't do a secondary bounce. Therefore, we also cannot do global illumination, which in Teardown you can see the dark roof here is very unnatural looking because we don't have that secondary bounce. The dynamic objects, updating the shadow volume, we already talked about also. I have a little visualization video for that where you can see the CPU working, which regions it updates. It's sometimes a performance problem, usually not because it parallelizes really well, but it does make the code very complex because you have to think about this in every aspect of the code. Every part of the code base needs to be aware of this. So you can mark a region dirty and then we combine these regions, and yeah, there's a lot of logic tied to that. That would be nice to get rid of. And the last limitation I'm going to talk about is the quantization artifacts. We already mentioned them. You can see them here a bit more in detail. Here's if we had perfectly sharp shadows, it would look something like this. You can very easily see these quantization artifacts that comes from resampling a voxel from rotated to axis aligned, and it's never going to be perfect, and you're going to see that. And the way we hide that in Teardown is to jitter the position of the voxels slightly for every raycast or every ray that we send to make the sharpest shadow you ever see is actually looks like this, which kind of masks out a little bit of those artifacts, but you can still see it if you know what to look for. So if we just put all these limitations side by side, it would be a list like this. And this is then naturally what we wanted to fix with the rendering part of the new engine. And this is also where I hand over to Gabe to talk about what we did for that engine.
All right. So the keen among you might notice that the bottom four of these limitations actually all relate directly to the shadow volume. So if we were to have another example of what the lighting looks like in Teardown, we can see these quantization artifacts. And ideally, what we would want is for the ability to have a precise ray intersection with our actual oriented voxel volumes. But in order to do that, we would need a completely new solution. So we decided to switch to the obvious, hardware ray tracing. And with that, we would get pixel-perfect shadows, really nice reflections, and even global illumination. But if we're going to have hardware ray tracing, we got to ditch OpenGL. And so we actually rewrote our renderer from scratch. And with Vulkan, we get a lot of nice things. Of course, hardware ray tracing, but also we have access to things like DLSS and FSR and denoisers like NRD. But Vulkan can be very daunting for a small team. So we actually went with an open source solution. That open source solution is DAXA. Any of you can try it out. And it was originally created by a friend of mine, Patrick Ahrens, who's in the crowd, and co-developed by Mathieu Sacmarie and me. DAXA allows me to have much faster iteration as it has a fully bindless resource model and very powerful render graph, as well as many other features, like completely removing the idea of frame buffers, of course. Or render passes, I mean. So onto how we actually ray trace. Here we have a couple of oriented volumes, and we still split the scene up into oriented volumes, just like in Teardown, of course, but with a slight difference on how these volumes are actually structured. And so we split these volumes up into a regular grid of cells that we call chunks. These chunks contain up to 8 by 8 by 8 voxels, and they are always positioned like relative to the origin of the object. So like as you resize the object, it doesn't actually restructure the grid. It will just expand it or shrink it. And so we actually insert all of those chunks, ABBs, as procedural primitives into BLASs, one BLAS per voxel volume, but with the ABBs tightly fitted to the geometry that's within that chunk. This matters a lot for inorganic stuff where, like flagpole, for example, where it's very vertical, and so you're not going to have it filling up the entire volume. And then, because we're using procedural primitives, we have to use a custom intersection shader to actually get the intersection. So here's a visualization of that custom intersection where we are just traversing through the volumes just like we do in Teardown with the fast voxel traversal algorithm, but with the MIP mapping concept removed. So because these volumes are so much smaller, we only need to usually take a few steps before hitting something or exiting out the volume again. But it's important to note, actually, that because we're using hardware ray tracing, we have no direct control over which of these volumes is going to get its custom intersection shader invocation first. It could be the case that we get the custom intersection shader invocation for this volume that's on the right before getting the one on the left, but that the one on the left had some geometry that was occluding it, and so then when it goes to do the traversal for the one on the left, it actually just wasted all the traversal work on the right because it was occluded. So we want a way to diagnose these kinds of issues. And one way to do that, you'd think, would be with Nsight. Nsight has a really, really nice traversal timing, or ray tracing debugger in general, but it also has a traversal timing feature. But unfortunately, because we're using custom intersection shaders, it actually just gives us the worst case scenario, basically screen space overlap of all of our AAVBs, because it doesn't have any knowledge of what our custom intersection shader reports. So while Nsight is super nice, it actually is not any use for us here. But we're not all hope is lost. So there's actually a super nice feature of SPUR-V, which is this intrinsic function available in both GLSL and Slang, which is clock ARB, where you can get a wave-wide clock counter for that wave. And so while it's low resolution, you can actually take a sample of the wave clock before and after before some expensive operation in any shader stage, as far as I'm aware, at any point. And so here, I'm actually just taking the clock value before and after, and then just remapping the difference of that to a heat map gradient. And when doing that, we can actually see that there are absolutely occasions where we are getting custom intersection shader invocations for geometry that is completely occluded. An important observation to make with this, though, is that when it actually trips over to showing some geometry behind is on a very large scale. It's showing a really large section. So that is a hint to the fact that the issue lies likely in our TLAS, either our TLAS generation or the hardware's traversal of that TLAS. And one of the biggest contributors to our TLAS are all of the volumes that are generated by terrain. Here's a section of terrain in Teardown, or from Teardown. And again, remember, because this volume is so large, it's all one grid, it gets split up as a pre-processing step by the level designers in order to minimize the amount of empty space that they would need to traverse through in Teardown. And this all these irregular shapes in our TLAS actually result in a much worse generated TLAS than if we were to actually just break up the terrain in a regular fashion and use those as our shapes, because we don't need that empty space optimization anymore because we already do the chunking, right? So that kind of covers how we can actually do ray tracing against our oriented voxel volumes. But what about the primary view? One very common question about Teardown is why don't we actually just rasterize the faces of all of our voxels with triangles? And the main reason is actually because there would just be way too many faces, and it would be way too much VRAM. Like on the order of gigabytes. So I actually didn't give up there. I actually was really curious if there was some way to rasterize voxels directly. And so one important thing to remember, one important optimization or observation that I had was that our chunk AABBs are almost like the same size as in world space as what traditional renderers have with their meshlets. And so I thought, why don't we just do rasterized view with full GPU-driven occlusion culling, and then just mesh all of these volumes on demand every frame for only the voxels that are visible. So if we take a look here, I have an example showing that I actually implemented this. So here, we're actually, in real time, remeshing all of the entire scene, basically, but only the visible voxels. And then I'm actually using specialized compute rasterization for the quads, because the quads get so small that it would be way too inefficient to hardware rasterize all of them. But unfortunately, even with all this effort, it was still too slow. It actually was slower than just ray tracing the primary ray. So I didn't stop there. I actually thought, I put all this work into having a full GPU-driven occlusion culling system. Why not try just ray marching into the chunk AVBs, which in hindsight probably should have thought that before. Would have been much simpler. And that actually was faster than this real-time remeshing, but still, even after optimizing the ray tracing performance, even on AMD, ray tracing primary was the fastest solution. So, with all of that, we now have all of these things crossed out, as well as kind of global illumination. Of course, I don't have enough time to talk about GI today, but we still have a very big issue, which is that indexed palette. And we really, especially our artists, wanted to be able to fix this. So we really wanted to be able to just, at runtime, recolor any voxel to be any color with any PBR properties, but we still need to be able to also expose geometry at any time through breakage, because we have explosions and such. So if we were to naively just use, we currently have 3 PBR properties: roughness, metalness, and emissivity. And then, of course, our albedo. So if we naively just had 6 bytes, or sorry, a single byte per channel, we would have almost 6 times as much VRAM consumption just from the level data itself. The reason it's not exactly, I will note this graph is not including the fact that we removed the shadow volume, of course. But it's not exactly 6 times, because both actually also have the bitmap for traversal, and there's a bitmap in Teardown. Anyways, what we actually do, again, is to split up the volumes to be sparse in VRAM as well. So there were many different choices we could have made between what those chunk sizes were. And you can see, actually, the one with the least VRAM is with 4x4x4 voxels. But rendering was actually faster with 8x8x8. So we kind of went towards tanking that extra cost of having a little extra VRAM so that we could have a unified splitting up between what we had in VRAM and what we actually used to render. And originally, I was going to wrap up this section of the talk here, but and just touch on that we were tempted by the VRAM savings that we could have got if we used block compression. Like, if we used BC7 to get 1 byte for our albedo and BC4 on each of our PBR properties, we would reduce the VRAM to almost, on average, match what we have in Teardown. But we always assumed that because our texels are so large, like you can see every single voxel in full clarity, we assumed that the artifacts of block compression were going to be too large to be like serviceable. But in preparation for this talk, I actually I wanted to make a visualization of what those artifacts looked like, of course. And so I integrated Compressinator from AMD into our engine, and the results were way, way better than I had expected. So here's an emblem from one of our levels, and it's the albedo. And when compressed with BC7, this is what that looked like. It's like almost identical. You can almost not see any difference. There's the difference again. So this got me super excited because that VRAM savings was super, super big. Unfortunately, lock compression, we need to be able to recompress our data in real time because we have explosions, we have the spray can as you saw, and so it turns out Compressinator is not very fast, at least for BC7, and so it actually wasn't fast enough to be real time. I ended up, because I got so enthralled in this, in the block compression, I got nerd sniped. I ended up also implementing a GPU solution with code that I stole from Microsoft. And unfortunately, the artifacts of their GPU version were much, much worse than what we saw in Compressinator. Again, here's what we had before, and then you can see all of the pink fringing around the end where there have to be endpoints that interpolate from blue to black to yellow, and those just are not collinear colors. So, unfortunately, BC7, for now at least, is not an option. But if we just use BC4 instead for each RGB channel, we actually go back to something that is serviceable. So with that, now BC4 for each channel, there's now an extra half byte per voxel, but with that, we have VRAM consumption that's almost identical, or maybe like up to 50% more than what we have in Teardown, despite having full PBR and albedo for every single voxel. And so I finally wanted to note that if we did include the fact that we got rid of the shadow volume, we actually have less VRAM, basically always, on all of our levels in this new engine. With that, we finally have the indexed palette issue solved. And so, I'll just leave you with a very beautiful video of how the engine looks today. Of course, when this project finally gets released to the public, I would love to be able to talk in much greater length about how we actually do lighting. I guess we can do questions.
Thank you.
Thank you for an awesome talk. Really cool to see the journey from Teardown into the new render and with the same content, but looking even better. Really awesome.
Thank you.
Oh yeah, so question over here. Oh, do we have someone with the microphone? You can use my microphone.
Cool. You showed the whole thing about using block compression to reduce VRAM usage. Did you also notice any performance improvements from using less bandwidth?
So there actually was, I did measure the performance improvement was only about like 1% on average. It's not really noticeable, and that's just because the main performance, the main like thing that's restricting our performance is the actual traversal itself, and the colors, like all the PBR properties, are only ever sampled once we get to our closest hit shader. And so there is no, there's a very, very minimal impact on using block compression on the throughput side.
Any other questions?
Hello. I was wondering if you thought about this concept, so Minecraft uses this now, where every chunk has a palette, but the palette is chunk dependent. So in chunks that have fewer block types, the bit of each individual voxel, like the bit size, is lower. Have you considered doing something like this as well?
For compression, yes, actually. If anyone knows me, I actually have. I actually was developing a voxel engine on my own before I started working at Tuxedolabs. And that's exactly what I did in my personal voxel engine. So I had, every chunk had its own independent palette, and it would compress, figure out the unique set, like losslessly, the unique set of all colors and normals and whatever per voxel properties there were, and then bit pack an index into that palette for each of the voxels. Yep.
Any other questions?
Oh, Niels?
Hey, thank you. Very good talk. So during the first part of your presentation, here, hey, you mentioned that you were building a G-buffer and you were lighting that, but that's not what you're doing here because you have transparency. Did you just switch to a full path trace solution? How are you handling transparency in this shot? Because didn't cover that.
That is something that is kind of up in the air right now. Transparency is a very complicated topic. The way that it's being done here is we actually send a G-buffer array in our main pass. Then if we happen to hit something that is transparent, we send a secondary ray that is refracted, and then what we output to our G-buffer is an actual like ray hit position, as well as the absorption that was applied. So you can actually have transparency, and you can only have a single transparency. The secondary ray actually ignores all transparent voxels when it traverses. And so like secondary rays for shadows and for GI are done with this special path where it ignores all transparency. But I really would like to get into that in the future when the actual solution is finished.
Okay, thank you.
I can add a little bit for context there that in the original solution for Teardown, transparency was handled by just doing a screen door effect with a checkerboard pattern in the G-buffer, and that was it. There was just one transparency level.
Are you going to make Teardown 2 with this new engine, or?
No.
Will there be a
had a
Teardown
lot
2
of
at all?
limitations.
Anybody else?
Yeah, over here. Unfortunately, I have another transparency question.
Oh no.
Might it perhaps help you guys to have access to the ray payload from the intersection shader?
For us specifically, no. No, we don't really need the access to the payload. We just return the voxel coordinate within the chunk from our payload, and then, from our custom intersection shader with a hit record. That's what it's, or what is it called? Hit attribute? I think
so, yeah.
Attributes, yeah.
Yes, the hit attribute. and send that over to the closest hit shader where we actually do handling of the transparency.
Okay, as you work on transparency more, if you have other ideas where you think that might help, let me know.
Okay.
Okay, we have one more question here.
Why didn't you stay with DX12 from Teardown?
What was that?
Why didn't you stay with DX12?
You mean it's switching the backend from OpenGL to DX12?
Yeah, well, Teardown has DX12 support. Why didn't you switch to Vulkan?
So the why we didn't? That's a good question. I think it was just a personal preference for both of us when we started to use Vulkan instead. So, but it's it's nothing more than that.
Yeah, the backend, the renderer that's in Teardown today is kind of a mess. So we would want to rewrite it anyways. Yeah. And so yeah, Vulkan was our choice.
And the reason it was rewritten to DX12 from OpenGL was mostly because of console support. So it wasn't really using a lot of features from DX12. It still largely resembles the same methods that was used in the original version.
Hi, over here. So thanks for the talk, first of all. I'm curious in terms of performance, since you have the same content running as the previous engine version, like what's the relative cost?
Full path tracing is a lot higher cost. As for primary, if you're curious about primary is actually faster than in Teardown. But full path tracing on even higher end GPUs can take like, I don't know, 10 milliseconds even. It's pretty rough.
Yeah.
Looks like we have another question over here. Could we get a mic?
Sorry, I'll just
Right
ask here, since I have the mic in the meantime.
Oh.
Do you see a benefit? There's two mics. Do you see a benefit in hardware support for voxel intersections? Or do you think with your approach you've solved enough of the issues for that with the custom intersection shader that it's not needed?
It's a good question. We actually talked to NVIDIA a little bit about this. I think this is maybe a bit too specific use case to do in the actual hardware. But some aspects, we haven't dug that much into it, but using custom intersection shaders at all is kind of a disruption of the whole flow of how the RT cores work, because they have to break in to do compute work in between. Both NVIDIA and ourselves were quite surprised by the performance level we got from this. So it's an area that's maybe not so well understood, and there are maybe some things that could be done to accelerate it, but I don't also see us really that much of a need for it right now, at least.
I would love hardware intersection for voxels. Nice. That would be awesome. I would not say no.
Hi, I wanted to ask about prior to going full hardware ray tracing, if you explored other solutions for reflections. It's quite an interesting problem to have accurate world space occlusion, but only screen space information for lighting. I know you didn't have global illumination at the time, but that would be, of course, no off-screen multi-bounce. I was wondering if there's anything you'd explored as a stopgap between full ray tracing, like what informed that eventual decision?
I did actually another thing in OpenGL before started on this new renderer that was maybe somewhere in between. That was kind of interesting. It was using, since voxel objects typically have a lot of these empty space, I was actually using that empty space, so just a single bit marking whether it's a voxel or not, and then we could use all that information in the empty space to encode things like the incoming light or the radiance, use that as a radiance cache basically.
Yes.
In the empty space of the voxel objects themselves. but it was a lot of problems with that, so I wouldn't really do it again. I don't know
All
if you
right.
have anything
I
to
think
add.
we have one more question and then we wrap it up.
Hello. I'm curious how many people worked on the rewriting of the whole engine and how much time did this took?
Just me and Dennis.
Yeah, we started on, or I started on it 2 years ago, but it's not just the renderer, it's really the whole engine, including all the frameworks. It's like the total rewrite. And we're working on it on and off a little bit, going back and forth. So it's hard to say, but in calendar time, it's been 2 years approximately since it started. But it's maybe more like 1 year effective time for the two of us.
Okay, awesome.